Okay, now I'm going to do that same titration, but with a weak acid. Weak, like you guys.
Exactly.
Yeah, you're pretty weak.
Damn.
Vinegar. This is acetic acid. So I am adding, this time, 12.0 milliliters.
Whoa,
Acetic acid, which is yes, it is the thing in vinegar that makes it smell like vinegar. There's various ways of writing this. This is a structural formula written very poorly. I have to write it out in order to remember the formula. There's 2 carbons, 2 oxygens, and 4 hydrogens. So sometimes you'll see it HC2H3O2, showing you that there's an H at the beginning. Sometimes you'll see it written CH3COOH. Chukoo! To show you that there's a carbon bonded to 2 oxygens, one of which has a hydrogen in it. So sometimes you'll see it where they're trying to show you with the "ku" on the end what the structure of this thing looks like. Sometimes they'll just put an H at the beginning so that you know it's an acid. Okay, I'm going to do HC2H3O2. Okay, that's vinegar. That's acetic acid. All right, my NaOH. Dang it, I got distracted. I was going to fill it up.
That's a lot.
Ooh, that could have been bad. Got to be very careful. That's another reason you don't want to try to go to 0, because the funnel takes a little bit of time to drain, and if you're trying to get to 0, your funnel might have some in there, you might go over. Okay? I am very lucky that it didn't go over, because if I had, it would have ran down the sides, and my choices would have been to either get 0.1 molar NaOH all over my hands, or drop this, none of which is a good option. Although, when in doubt, drop it. Don't sacrifice the body, sacrifice the glassware. By drop it, I don't mean like throw it as hard as you can like it's a grenade. You just like set it down, or set it down gently, carefully, wash your hands right away, and then get a spill kit. That's me. I'm not trying, but if it happens. Okay, so I went below 0, that's okay. As long as I know where I start, which... Huh? Oh yeah. Direct clamps. Okay, I'm starting at 0.65 milliliters. 0.65 milliliters. Okay, so let's add the vinegar. Let's add a little bit of indicator. All right, now let me let you in on a little secret about titrations. If all we are really interested in is what is the concentration of this acetic acid, well, we've got a problem here. If I was using a pH probe, this would be impossible, right? Okay? But what I can do, I can add water. Because I haven't changed the amount of acetic acid that's in here, right? Now it is going to change the shape of my titration curve, my pH curve a little bit, but again, if all I care about is adding enough NaOH to completely react with the acetic acid that's in there, it doesn't matter how much water there is, right? Okay, so we still have the same amount of acetic acid in there. let's titrate. Boring, 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 boring. Boring, boring. Eventually it'll just go from boring to terrifying. Raise it up. Now, another thing you have to be very careful of when you're doing a titration is to make sure that you don't go over 50. Otherwise, you have to start over. Because there are no marks past 50. So as soon as I go over 50, I'm no longer able to record volumes. That's a problem. Okay, it's getting a little orangish, but not all that orangish. Coral. Coral. Alright, I'm getting scared, so I'm going to stop there. And I'm going to read the volume as 48.08. Okay, that's batch 1. Now I'm going to add more NaOH. Why is it taking so long? Probably because the acetic acid must be fairly concentrated. We can tell already since it's taken more than the volume of acetic acid that I put in.
Wash your hands. Drop it.
You're
very neat. Nice job.
Burning my skin. That's how you know it's a sugar. Okay. So, number 2, we're starting off here. What? 7.0. 7.00 is my start.
The second side?
The second start. Woo! Okay, it's getting orange.
There's stuff coming out.
We're hoping for our yellow. I'm keeping track. I'm at about 31. I do not want to go over. Otherwise, you'll have to start over.
Pretty yellow.
Yellow. It's yellow.
Hear that? It's dangerous.
49.60.
Dang, that was a close one.
Yes, living on the edge. All right.
Oh, that's how you meant 50. I was like 50 on the Erlenmeyer class?
No, I can't go over 50 on the burette because there's no markings in it. Another reason we pour into beakers. Beakers have a beak. And the beak allows us to pour without spilling. So.
For the lab, isn't everyone going to use like the entire bottle? Do you need that much?
I'm going to use different concentrations so you won't have. But yes, sometimes if you absolutely do not know what it is, it could take a very long time.
Oh my god.
Okay, ooh, I almost didn't read the initial. That would have been a
Wow.
Woo!
Look at this man.
5.70.
You almost destroyed everything.
That's right.
5.70.
Now, we're spending a lot of time doing things that I wasn't really planning on doing, but
Hey.
Hey, yo, I thought we were looking for yellow.
Yeah.
What, now you just...
Why is it tornado like so
no English in it.
Okay, alright, slow down there.
idea that everyone's like, why are you doing that?
Yeah.
Why do you have to stop?
Okay, so, we like it?
No.
Sure, it's green, just because we want to move on. 16.00.
Nice.
Okay,
That's a lot of numbers.
so now we gotta do all those changes in volumes, add them together, and figure out what total volume.
100.33.
Can somebody confirm?
No,
100.92. It's probably me.
Oh, you actually did put them in?
Yeah.
Or it's my terrible handwriting.
I got 100.3.
That's
Alright, let's just go with 100.33. Okay, so now here's one very important point. In this titration, we are not adding a strong acid and a strong base. So the equation that we're going to work with is not the equation that's up here. This is a weak acid strong base titration. We know that when we put acetic acid in solution, when we shrink ourselves down, what do we find?
what?
Think back to that simulation. If we have a weak acid in solution,
Not all of it dissociates.
not all of it, in fact, very little of it dissociates. Actually, I'm not going to use the term dissociates because that's Arrhenius model. Very little of it actually donates its proton. So really what we find in solution is not H3O plus, but mostly still HC2H3O2. Okay, but that being an acid can still donate its proton to OH minus. It will form H2O plus C2H3O2 minus. So this would be the net ionic of a weak acid strong base titration. Now it's not going to affect the calculation we're doing right now, which is trying to figure out the concentration of the acetic acid, but it's going to affect calculations we're going to do in a moment. So we've added, let's see. We had 0.100 molar NaOH. We've now added 0.10033 liters. So we've added 0.010033 moles. Agreed? Okay, because of the stoichiometry, 0.0013 moles of OH minus must have reacted with 0.001033 moles of acetic acid. The volume that we had originally was 0.012 liters. So what's the concentration? Wait, I added a zero. Come on, Paul. Way more concentrated. The other thing, the HCl we were adding last time was 0.03. This is 0.8. So over 10 times more concentrated, right? So it took more volume, that's okay. All right. Now, when we do these calculations, let's do some calculations for some various points during the titration. Let's see, it took 100. So let's do 25, 50, 75, 100. And 125. I hope that my phone has enough space to first of all, can we calculate the pH with no NaOH added? Well, before we added NaOH, all we had was acetic acid, right? What does acetic acid do? Gives away protons. Who's it going to give it to? I haven't even added NaOH.
H2O.
H2O. I still have water in there, so we know that this reaction will occur. What we don't know is what is the K for that reaction. So we got to look it up. The old internet tells me it's 1.8 times 10 to the minus 5. Put that down a little bit. Why did I put that down? I forgot to save room for my ice table. Now we calculated that it originally started out at 0.836 molar. We don't care about water. We always assume H3O plus. The other thing are 0. This is going to go down. These are going to go up. So 0.836 minus x, x, x. If my Ka expression is the concentration of H3O plus times the concentration of C2H3O2 minus over the concentration of HC2H3O2, then 1.8 times 10 to the minus 5th better equal x times x over 0.836 minus x. Solve it. Okay, so when I graphed it and found the intersection, I got 0.00387. Rochelle got it?
Yep.
Anybody else? Okay, so the A's have it, or the N's have it. So what does this tell us? It's the change, which because we assumed H3O plus and the acetate ion here started out at 0, those are the equilibrium concentrations of those. Well, if this is the equilibrium concentration of H3O plus, all we got to do is take the negative log of that to figure out our initial pH. What do we get? 2.41. Agreed? Just the negative log of that. Because in our ice table, that is the equilibrium concentration of H3O plus. Okay? So again, if we compare, well, it was more concentrated weak acid when the pH is higher than the less concentrated strong acid. Does that make sense? Right? The 0.03 molar HCl started at 1.5. we calculated the initial pH for our strong acid titration, it was lower than the initial pH for our weak acid titration, even though the strong acid was less concentrated. Okay, so remember there were some things we were supposed to learn during that simulation. To actually get the same pH, we would have to have a much, much higher concentration of weak acid than of strong acid to have equivalent pHs. Okay, so it makes sense that we're starting at a higher pH because we have a weak acid. It doesn't completely dissociate. Okay, what about 25 milliliters? What are we going to do? Well, the process for doing these titrations is twofold. First, we have to do a stoichiometric calculation here. We have to figure out what was the limiting reactant, acetic acid or hydroxide. Then, once we know what we have excess of, then we can start to think about what sort of equilibrium reactions are going to occur. Okay? So, let's redo this calculation with 25 milliliters. How many moles of OH minus have we added? 0.0025 moles of OH minus. Okay, but we know this, the acetic acid, was 0.836 molar, and we know we started with 12 milliliters, right? So how many moles of acetic acid did we have in there? Okay, so who's our limiting reactant? OH minus. Okay, so now here's the thing we have to think about. How much of this acetic acid is left? Well, if this is how much we had to start, we know we're going to completely use up that much hydroxide, and this is going to go down by the stoichiometric amount. So how much will remain? And what's our total volume of solution right now? There was 12 milliliters to start. We added 25 milliliters of NaOH, so 37 milliliters is our total volume, or 0.037 liters. So what is the concentration of acetic acid remaining? Okay? So it's just like a limiting reactant problem. This might look a little weird. In fact, it does because it's all over the place. I apologize for that. But essentially what I'm doing is I'm using the molarity equation to figure out how many moles of hydroxide and how many moles of acetic acid I've added. I know the hydroxide is less, so it's limiting. So because there's a 1-to-1 ratio between acetic acid and hydroxide, to use up all this hydroxide, I'd have to use the same amount of moles of acetic acid. So then I just subtract that from how much I have, tells me the moles remaining, then I gotta be careful, I gotta divide by the total new volume of solution, and that gives me a concentration. When I go back into my ice table here, now at 25 milliliters, I'm actually starting with 0.204 molar acetic acid. But we have something else that we have created. Because now our products are not just H2O and H2O. Now we've got acetate ions as a product, and acetate ions are part of this weak acid equilibrium. So they should not be assumed to start at 0. We know we're going to create some. How much are we going to create? how much acetate, C2H3O2 minus, have we created? Well, if we used up 0.0025 moles of OH, and there's a 1-to-1 ratio, that means we've created 0.0025 moles of acetate. Okay, so this, we know we've created 0.0025 moles. Our volume is 0.037 liters. So what's the initial concentration of acetate? Okay, so this is going to totally change our ice table. Now we're going to have 0.204 minus x here. We're going to have 0.067 plus x here. Solve it.
So why is it that zero?
Because we know that it's a product of this reaction. So it's not like we're just taking acetic acid and dumping it into water and seeing how much product or how much of this is formed. We've actually formed some during the titration. So if we figure out how this equilibrium is going to sort of result, we have to figure out how much acetate we've actually produced during the titration and put that in as our initial amount here. So we have to figure out how much of this remains, and we have to figure out how much of this we produce. And those go into our ice table.
Because it's weak acid.
Yep. Woo! Thanks, science, for that graphing function. Unless you want to do this algebraic.
Yeah.
Who's got fast fingers?
5.47 times 10 to the negative.
Anybody else get that? That's what you got too? How about a third? Okay. So if that's our x, and now our x still tells us the equilibrium concentration of H0 plus, take the negative log of that. What do we get? Somebody confirm that? Yeah. Now, for 50 milliliters, I want to tell you a little shortcut. There's an equation on your equation sheet, the second one to the end on the equilibrium. 50 milliliters for this titration represents a special point on the titration curve. We know that 100 milliliters is our equivalence point, right? So that's where the pH should be rapidly increasing. Well, if 100 milliliters is the equivalence point, then 50 milliliters is the very appropriately named half equivalence point.
Oh, wow.
Because we've added half as many moles of OH minus as we had of our weak acid to begin with. What that means is, if we started with 0.01 moles of acetic acid, well, at 50 milliliters of NaOH, we've added half that number of moles of NaOH. What's going to happen then is that the concentration of this is going to be the same as the concentration of this. We've turned half of this into that. So if we had 0.01 moles of this, now we'll be at 0.005 moles, but we'll be at 0.005 moles of this as well. So these two concentrations are going to be the same at the half equivalence point. And if you look at your equation sheet, it says the pH is equal to the pKa plus the log of the ratio of the A minus, in this case the acetate ion, over the acid, in this case acetic acid. Well, if these two concentrations are equal, what's the ratio? 1. What's the log of 1?
0.
0. So at the half equivalence point, we're talking about the second to last equation in your equilibrium section. pH equals pKa plus the log of that ratio. We said the log of that ratio is 0. So pH equals pKa. What's the pKa?
Negative.
Negative log of Ka. What's the negative log of 1.8 times 10 to the minus fifth? 4.74. So it's gone up very little. Okay? We're going to see that shape. We get an increase, then we get a leveling off, and then we get that really sharp increase, and eventually we level off again at the top. Okay? So at the half equivalence point, pH equals pKa. Now, interestingly enough, we could have used that same equation to calculate the pH here. Because we knew the ratio of the A- form and the HA form. What's the log of this ratio? What's the log of 0.067 over 0.204? The log of this over this. It should be a negative number. Negative 0.43. Well, if our pKa, what did you say it was? 4.7. 4.7 minus 0.43 gives us 4.7 minus 0.43, the pKa minus the log of that ratio. 4.7 minus 0.43 is 4.27. That's about what we got when we did that whole ice table thing. Okay? So that's sort of a shortcut equation that allows us to calculate those pHs without going through the whole ice table thing, although it is an approximation. Okay? If you have a K value that's too big, that approximation doesn't work very well. Okay? Because it's not really factoring in the plus x's and the minus x's. Well, x is really small compared to those initial concentrations, so that's why that approximation works. Okay? Now, what about at 100 milliliters? pH is not 7 at the equivalence point for this titration.
8.
Why not? Because what we have left in solution at the equivalence point of this titration is not just H2O and H2O. It's H2O and this. What's this? It's a conjugate base. So the pH is actually going to be above 7 at the equivalence point. So actually, if I have green here, I might not actually be at the equivalence point. Okay? Well, let's figure out what the pH should have been. Well, if we knew how many moles we had in there originally, we know at the equivalence point we've added the exact same number of moles of OH, right? So this should go to 0, OH should go to 0. Now C2H3O2 should have that same number of moles. Does that make sense? At the equivalence point, we've converted all of this into that. So that's why I just took the moles of weak acid that I started with. At the equivalence point, that's how many moles of its conjugate base are present.
But if we solve this, are we going to find out that it's 7 because we just assumed that 7 was the equivalence point in the first place?
No, we didn't assume it. We knew that what was formed in the strong acid, strong base is water, and water undergoes its own equilibrium reaction. So I could have made you make an ice table for water, reacting with water. We know the K for that is 10 to the minus 14th. When we solve it, we would get an H3O plus concentration of 10 to the minus 7th, which is why the pH is 7. We're We're not assuming it, we're actually calculating it based on the autoionization of water. But now in this titration, water's not the strongest acid or base left in solution. This is the strongest thing left in solution, so this will affect the pH more than the water does. Okay? So, 0.01 moles, what's our volume right now? 112.33, I guess. So what is the concentration of the acetate now? Somebody confirm that?
Yeah.
Okay, what are we confused about right now? Well, I can't help you with that. You're a human being. You've been in school for 12 years now. Not confused about everything. If you can't ask a more specific question, I can't help you.
Can you go over how you got the 0.11233 again?
That was the initial volume. Every time when I'm finding the concentration, I'm taking the initial volume that I added of the weak acid and however many milliliters I'm adding of the NaOH. So I want to know the pH at the equivalence point. That was 100 milliliters. I'm adding it to the 12 milliliters that we started. So 112 milliliters.
So should we just know for a weak acid to figure out the initial concentration for this?
For a weak acid, to do a titration calculation, you first have to do the weak acid strong base as a just normal stoichiometry. But then once you know what's still in the solution at that point, you have to plug it into an equilibrium reaction to figure out the pH.
And that's the pH of
The solution, the mixture.
of the nitrogen.
Now, this is going to get more complicated because this equilibrium no longer applies. We don't have HC2H3O2 in the solution, we have C2H3O2 in solution. What does that do? It's going to grab a proton from water, reforming this, and what's left when it rips an H off of water? OH minus. So now we can plug into our ice table. This is 0.0893. We don't care about water. These we assume they start at 0. Minus x, plus x, plus x. 0.0893 minus x, x, x. However, we got another problem. This is not an acid, so we're not going to use the Ka. This is a base. We need its Kb. How do we get the Kb? We use Kw over the Ka for the weak acid that it came from. That gives us our Kb. So that's going to be 10 to the minus 14th over 1.8 times 10 to the minus 5. That'll give us our Kb. Then hopefully you know how to solve for x. And then just be careful that x is now our equilibrium concentration of OH minus, which if we take the negative log will give us the POH. And then we do 14 minus that. So let's try to solve that in the next minute and a half.
Okay.
You can't do
So
it.
you're gonna solve for pH, and then you're gonna get to pH. You do 14.
10 to the minus 5.55 times 10 to the minus 9 is what I'm getting for my Kb.
Wait, what are you getting?
5.55 times 10 to the minus 9?
Yeah. Well,